Welcome back. Today we are covering section 7.1, which will be on your second test. It's integration by parts. And we say the integration of u dv is equal to u times v minus the integration of v du. So we say, well, where does that come from? Well, if I start off with a uv, and I decide I want to take the derivative, it's a product, so I get uv prime plus vu. Oops, vu prime. And then I could say, oh, I'm going to integrate both sides. I'm going to integrate each bit by itself. After doing that, the integration of the derivative of uv is just uv. And then I have this here, which is u dv plus v du. That's great. I can move everything over and I end up with the integration of u dv is equal to uv minus v du, which is the formula we're going to use. So the question is, how do I know how to do this? Because I have two things I don't know how to take the derivative of. They're a product. So since they're a product, I could break them up by using what's called lipids. This is not a standard form. It's a nice little acronym that somebody came up with that helps me. It should work about 90% of the time. So the L stands for, if I have a logarithm, I'll make that my u. This is what do we pick to be u? Then I go down my list. If I don't have a logarithm, do I have an inverse trigonometric function? If I do, I'll pick that to be the u, and then the rest will be the dv. If I don't have that, then I'll look at a polynomial. If I don't have polynomials, then I'll look for exponential functions. And if I don't have that, then I go to trigonometrics. And that should cover the basis. Now, will this work again? It should work 99% of the time. There's some rare cases it doesn't, but it's a nice little trick that helps you. The book doesn't tell you to do this. It's more trial and error, and pick whatever you think might be easier to take the antiderivative of. So let's start with this problem. So I have an x times a cosine 3x, and I'm going to use my lipids, so LIPET. Do I have a log? No. Do I have an inverse trig? No. Do I have a polynomial? Yes, I have an x there. So I'm going to say let u equal x. Let's take the derivative of that. Du is equal to just dx. Well, dv has to be what's left over. If this was u, this has to be dv. So my dv is equal to cosine 3x dx. So that means v had to be 1/3 sine of 3x. So now we have a u, a v, a du, and dv. So we can now say that I have what I was looking for. This is the u dv part. I'm going to now build this part, the uv times the integration of v du. So I take u times v. U is x, v is 1/3 sine 3x. From that, I'm going to subtract the integration of v, which is 1/3. I like to put my constants on the outside, sine 3x, times du. Well, du is just dx. And I'm going to look, can I integrate that? Yeah, I think I can handle this. So I have 1/3. I'm going to put the x in the numerator here, sine 3x. Take the integration of this, 1/3 minus cosine 3x. I need another third to handle that 3x part. So then I'm going to multiply through, and I get x over 3 sine 3x. A negative times a negative is positive. A third times a third plus 1/9 cosine 3x. This is an indefinite, so I have to remember to put the c, plus c. I will take off on the test if you're not giving me plus c. right? And that's how we apply Lipitz, and this is how we use integration by parts. Here's another one. I'm going to go to Lipitz again, L-I-P-E-T. Do I have a log? Absolutely. So we're going to say this is my U, and that's my dV. So let U equal the natural log of x. du is equal to 1 over x dx. dv is just dx, so v has to be x. So now I have u times v, x, the natural log of x. That's my u times v. Subtract from it my v, the integration of my v, x, times my du, 1 over x dx. Cleaning it up, I have x, natural log of x, minus the integration of dx. That's an easy thing to integrate. I have x, natural log of x, minus x, and do not forget my c. So plus c. What's interesting, though, is sometimes we work through these problems and, well, we don't have what we want, and we have to, I still can't integrate it, so then I have to go a second time or a third time. So let's look at this problem. Using Lipitz again, L-I-P-E-T. Do I have a log? No. An inverse trig? No. A polynomial? Yes. Let u equal x squared. du then has to equal 2x dx. dv, right? If this was u, this has to be dv. dv, sorry, my u's and v's look very similar to each other. Sine 3x dx. So v has to equal the opposite of 1/3 cosine 3x. So now I have my u's and my v's. I want a u times v, so I have x squared over 3 negative cosine 3x. Subtract from it a negative 1/3, so I'm going to make this a plus. Integration cosine 3x. My du is 2x. I'm going to put the 2 on the outside. X dx. So take a second, look, all I did was fill in the blanks, and now I have this. But the problem is I look at this and I go, well, I'm not quite sure how to integrate that. So what do? We're going to apply parts again. And so we're going to say Lipitz one more time. No log, but no inverse trig, but I do have a polynomial. So I'm going to say let u equal x. du is equal to dx. dv has to be what's left over, which is the cosine 3x dx. So v has to equal 1/3 sine 3x. I'm going to move this over so it's not in the way. I'll just rewrite it over here. There. So what I'm building this time is this. I'm going to work only on that part. So I have plus 2/3 times. Instead of the integration, I'm replacing that. I have to have a u times v. X over 3 sine 3x minus 1/3 the integration sine 3x dx. This I can handle. I know how to integrate this bit here. Remember, this whole thing is that bit there. So I'm going to, this is one of these problems, it's a bookkeeping problem. You really should get highlighters, it helps. I have 2/3 x over 3 sine 3x minus 1/3. When I integrate sine 3x, I have to have a third. I have a minus cosine 3x. So I'm going to distribute 2/3 x over 3 sine 3x plus 2, oh, sorry, I can do math, plus 1/9 cosine 3x. I will now distribute all of this, and I get 2x over 9 sine 3x plus 2 over 27 cosine 3x. I don't want to forget all of this. That needs to come down. And that was a minus x squared over 3 cosine 3x. And I was adding that part. So this here took care of that piece. And then this is what was left over. So as you can see, this can get messy, and I'm still missing one little piece. Let's see, because it was an indefinite. They can get long, and sometimes we don't get a nice answer like this. Sometimes we work out these problems, and they just don't work out. Let's do another problem. Lipids. Log, no, but I do have an inverse trig. So I'm going to let u equal the arctan of x. Du then has to equal 1 over 1 plus x squared, and yes, you're supposed to know that. dv is what's left over, dx. So v has to equal x. Using my integration by parts formula, u times v, x arctan of -1, or of arctan of x, subtract, I'm integrating from 0 to 1, x over, right, because v times u, du, 1 plus x squared dx. Now, what do I do? Well, first of all, I have to figure out how to handle that. And I could do, hopefully you guys are seeing this, I can do a u substitution. I could say let, or w substitution in this case, let w equal 1 plus x squared. If I do that, then dw is equal to 2x dx, or 1/2 dw is equal to x dx, because I don't have that 2. So just looking at what's on here, 1 to 0, I am not changing the limits of integration. I need that 1/2. Instead of having x over 1 plus x squared dx, I rewrite as 1 over w dw. This is something that we had learned to do in Calc 1. I can then, don't forget to bring this part down, x arctan of x. I then leave the left-hand side alone. I'm going to integrate. 1 over w is the natural log of the absolute value of w. And I'm going to evaluate that from 0 to 1, not -1. But I don't want to evaluate w, right? Because we didn't change the limits of integration. So I want to put back. And the reason I couldn't change the limits of integration, I still have things in terms of x also. W is 1 plus x squared. I'm evaluating everything from 0 to 1. So I have 1, the arctan of 1 minus 1/2 ln of 1 plus 1 squared, subtract 0 times the arctan of 0 minus 1/2 the natural log of 1 plus 0 squared. This goes to 0. This will go to 0. And I'm left with pi over 4, because the arctan of 1 is pi over 4, minus 1/2 the natural log of 2. And I can drop the absolute value signs because 2 is a positive number. And that's my answer. So that's the only one that we've done so far. And if you see, this is rewritten as one fraction. This is the first one that we've done so far that that required us to evaluate. Let's look at another one. Now this is a little tricky one. I could say, well, using Lipitz, logs, let u equal the natural log of x being squared. Du is equal to 2 times the natural log of x times the derivative 1 over x. dv, that's just dx, and v is equal to x. I can then combine u times x, natural log squared of x, subtract v du. Put my 2 here, natural log of x, 1 over x, dx. So this cleans up nicely. X, the natural log squared of x, subtract 2, the integration. When I pay attention, this and that will cancel, give me the natural log of x dx. Well, if I look at this, we haven't learned how to integrate the natural log of x, so we are going to use integration by parts again. So we're going to let u equal the natural log of x, du is equal to 1 over x, dv is equal to dx, and v is equal to x. So we're going to now leave the left-hand side alone. And then we're going to replace this as a parts problem. So I need to have u times v. So I have x natural log of x, subtract the integration of v du, which is x times 1 over x dx. That's going to clean up nicely. X, the natural log squared of x minus 2 times the quantity x, natural log of x minus the integration of dx. I'm going to take some time here, and left-hand side again is being left alone. I have a minus 2 times x natural log of x, and derivative of this is just x. Derivative of dx is x. Last thing I need to do is distribute my 2 and add my constant, because remember, this is an indefinite integral. And don't forget my plus. As you can see, these get long and they get very tedious. Let's look at this problem. I'm going to let u equal the natural log of x. That's what Lipitz would tell me to do. Du is equal to 1 over x. dv is what's in the denominator, and that's x to the minus 2. So v has to equal minus x to the minus 1. I forgot my dx here. So I'm going to build this up. U times v, minus 1 over x, natural log of x, minus v. Well, there's a negative for that v value, so I'm going to put that there. Make that positive. 1 over x times 1 over x. Right, v is X to the minus 1 is 1 over x dx. Cleaning it up, I get this 1 over x squared dx. Well, the good thing is I know how to take the derivative of 1 over x squared. And that becomes minus 1 over x. And I don't want to forget my c. We only have 2 more problems, and these 2 problems get really interesting. This is one of these where we'll apply L'Hopital's, and we're not going to, not L'Hopital's, I'm sorry. We're going to apply integration by parts. And we're going to say, I don't know how to integrate that. I apply integration by parts again. And I don't know how to integrate that. And we're going to continue to do that over and over and over until we find a pattern. So we'll get ready to do that now. Okay, so let's go on to the next problem. E to the 2x cosine 3x. We're going to go through Lipitz. We don't have a log. We don't have an inverse trig. Polynomial exponential trig. Well, it looks like an exponential, e to the 2x. So we're going to say let u equal e to the 2x. du has to equal to e to the 2x. dv has to be what's left over, cosine 3x dx. V has to equal 1/3 sine 3x. So we have our u's and v's, and I can build this up. U times v gives me e to the 2x all over 3 sine 3x. Subtract from that v du. So I have a minus 2/3 integration e to the 2x sine 3x dx. When I look at this, I go, oh, that's easy. I can't do this problem. All right, I'm going to look at it and say, I don't know how to integrate this. Well, we're going to do what we did last time. We're going to just find another way of applying integration by parts. So I'm going to say, let's change color so we don't get lost. Let u equal e to the 2x. du has to equal to e to the 2x dx. dv has to equal what's left over, sine of 3x dx. V has to equal 1/3, minus 1/3, sorry, cosine 3x. Because the derivative of cosine is a negative, so I need a negative in front to make sure I get a positive sign. So I have this minus 2/3 out front that I have to multiply everything through by. My u times v, minus e to the 2x all over 3 cosine 3x. Subtract my v. Well, there's a negative 1/3, so I have a negative, and then my v times u, my v times du. When I combine that, I get a 2/3 integration e to the 2x cosine 3x dx. I look, and I stop for a second, and I notice, hopefully, that this looks an awful lot like this. Because if we notice that, if I can do this over and over and over again, and I'm going to go on to the ends of time. But I notice at this point that I have where I started. So before I go any further, I need to distribute everything. So I have the negative 2/3 times that minus e to the 2x. So that gives me 2 e to the 2x over 9. And then I have the negative 2/3 times this, which is a minus 4/9 times the integration of e to the 2x cosine 3x dx. So I've distributed, going back here, this is now taking care of all this. So I need to add back everything, including the original integration symbol. So I start off with the integration of e to the 2x cosine 3x dx. So hold on for a second just so that we're all on the same page. This is coming from that. This piece here, I need to add back in. Equals e to the 2x over 3 sine 3x. And then I got to continue with the rest of my problem. Plus 2 e to the 2x over 9 minus 4/9 integration e to the 2x cosine 3x dx. And again, that just happens to be, that's what I added back in. Well, it's an equation, and an equation allows me to move things. So what I'm thinking about doing is taking this part here. Whoops, sorry, it's too much. Taking this part here. Let's see if I can do this. Taking this part here and moving it to the other side of the equation. So I'm going to add 4/9. 1 plus 4/9 is 13/9 e to the 2x cosine 3x dx. Again, I took this part here and added it to this part here. They're like terms. And that's now equal to e to the 2x over 3 sine 3x plus 2 e to the 2x over 9. Well, we're almost done. I started off with the integration of e to the 2x cosine 3x. I have a 13/9 here in front. I don't want that 13/9. So I'm going to multiply everything through by the reciprocal. And when I do that, e to the 2x cosine 3x dx. Oops. Is equal to 9 over 13 times e to the 2x over 3 sine 3x plus 2 e to the 2x over 9. Well, this math is simple. I could do that, so I'm going to do it real quick. 3 e to the 2x over 13 sine 3x plus 2 e to the 2x all over 13. And hold on for a second. Did I lose something? Yes, I did. Where'd it go? E to the cosine. Hold on. I have an error here. Give me a second and I'll find where I made my mistake. Okay, I see where I made my mistake. I lost this right here. So I should have a cosine 3x there, which gives me a cosine 3x there, which gives me a cosine 3x here, and that gives me a cosine 3x there, and my final cosine 3x here. And then I would want to remember to add my c. I apologize for that. As you can see, it's totally about bookkeeping, and it's easy to lose things when you're doing this. Again, I strongly suggest having highlighters, and I should have been a little more careful. I apologize for the mistake. This is our last problem. Why don't you pause the video and try it yourself, and I'm going to do it also. So I'm going to pause the video, and I'm going to work it out, and then hopefully you'll come back and see my answer. I was going to pause this, work out the whole problem. I'm thinking That's probably not a good idea. Let me talk myself through this so you see what's going on if you've made a mistake. So let's start what I have written down so far. I'm going to let, by Lipitz, I'm going to let u equal e to the x and du equals e to the x dx. dv would be the rest of the problem, so that would make dv is equal to sine x dx, and v is equal to the opposite of cosine x. Building up my uv, I get a minus ex times cosine x plus my v du. Well, my v is a negative, so I'm going to put it as a plus instead of a negative. Plus the integration of e dx cosine x. This is one of these problems where if I'm paying attention, I can't work it out, e dx cosine x, but I could redo this as far as parts go. I can let u equal, let me change the thickness of this pen, u equal e to the x, du is again e to the x dx. dv is equal to sine x dx. V has to equal, whoops, sorry, I looked at the wrong part of the problem. dv is equal to cosine x dx. V has to equal sine x. So I'm going to build up my problem again. I have a minus e to the x cosine x. And then I'm going to do my uv plus e to the x sine x minus my v du. E to the x sine x dx. And again, like the problem we just did on the last page, this looks just like this. So I could then do a nice substitution or manipulation of the equation. So I want to rewrite the whole thing. The integration e to the x sine x equals, right? Because the whole time this thing was equals minus e to the x cosine x plus e to the x sine x, subtract the integration of e to the x sine x dx. When I add the e to the x to both sides, I get 2 times the integration of e to the x sine x is equal to minus e to the x cosine x plus e to the x sine x. I don't want this. I want to multiply everything through by a half because I want to clear out the 2. Now, sometimes people will put the c here, and that's fine. You can put the c now. When I multiply 3 by 2, I get this e to the x sine x is equal to 1/2 times minus e to the x cosine x plus e to the x sine x plus c. Distributing the 1/2 to the x cosine x plus 1/2 e to the x sine x plus c. You notice I didn't write c over 2. C is a constant, whether I multiply by half or some other number or not, no other number. It's still just a constant. So there's your answer, and we are done. This is the last problem for section 7.1. Chapter 7 is a long chapter. We'll break that up into 2 tests. It'll have the L'Hopital section, which we just did previously, 7.1, 7.2, and 7.3. And what you're going to see posted online will be an integration sheet or a sheet with some stuff that you need. That will follow you from test 2 on, including the final. And it just has some tips. It has some stuff that you need to know about the integration that you do not have to memorize. All right, this concludes today's video, and hope you have a great day and look forward to seeing you in the next class.